time. Now, relative time is simply saying that the red wall limestone down here is going to be considerably older than the coconut sandstone, simply because it's below it. But absolute time, the topic of this podcast, involves saying that the red wall limestone is 335 million years old. Well, let's start with the Earth. How old is it? The first answers came from religion. Jewish calendar says that the Earth began 3760 BC. Bishop Ussher looked at the Bible in 1650 and concluded that the Earth was formed on the evening of Sunday, October 23rd, 404 BC. Now that answer is surprisingly specific. Doesn't mean it's correct, because the problem is the Earth requires time to create the geology that we've seen. We learned that from James Hutton, the father of modern geology. Looking at this angular unconformity at Siccar Point, he recognized that the processes of deposition, lithification, tilting, uplift, erosion, and more deposition, lithification, uplift had to occur to make this formation. And that takes a lot more than 6,000 years. Some people started to determine the age of the Earth by more scientific methods. One of those was the Comte de Buffon, who got a hot iron ball and calculated how long it took to cool, assuming that the Earth was once hot as it was, and he came to the conclusion that the Earth could be as much as 75,000 years old. Later, Lord Kelvin did a similar kind of experiment, but with much more understanding of thermodynamics, and he concluded the Earth was 20 to 40 million years old. Unfortunately, that's way too young for the Earth. The geologists of his time knew it was wrong, but although his calculations were flawless, he couldn't know about one important difference. That is that the Earth heat was a result of the Earth's formation, as he assumed, but it is also the result of radioactivity, and Kelvin could never have known about that. As it turns out, radioactivity is the key to absolute time, because we use it for radiometric dating. Ever since 1950, we've been able to figure out the rate of decay of elements found in minerals and use that to date the rocks in which those minerals are found. Radioactive decay is the spontaneous process in which an isotope, the parent, loses particles from its nucleus to form an isotope of a new element, known as the daughter. If you remember, an isotope is a form of an element with an unusual number of neutrons. For example, carbon-12 has 6 protons and 6 neutrons. It's a very stable atom. But there is an unstable radioactive form of carbon that has 6 protons. It has to, or otherwise it wouldn't be carbon, but it has 8 neutrons. A nuclear reaction is constant, and that is why we can use nuclear decay as a method of timing things. We measure it in half-lives. A half-life is the period of time it takes for half of a substance to undergo decay. So if you start off with all of your parent atoms, after one half-life, you'll have half. But if you have another half-life, it doesn't totally decay. Instead, you will have 1/4, and then 1/8, and so on. So this is a classic exponential decay curve. It never actually hits 0, it only approaches it. As the half-lives go down, you get the whole parent, half, quarter, eighth, and so on. You can talk about this mathematically as being 1/2 to the number of half-lives, known as n. Or if you want to talk about the percentage of the parent remaining, 100 times 2 to the n. Let's take a look at a zircon crystal. Zircon is a silicate mineral. As zircon forms, it tends to take in uranium, but it does not take in lead, and that works out very nicely because these two radioactive isotopes of uranium will decay into lead. So the uranium-238 decays into lead-206. At the same time, the uranium-235 decays into lead-207, each of them with their different half-lives. We start off 4.5 giga years ago, that is billion years ago, you would have all your 238 and your U-235, but no lead present in the zircon crystal. 4.5 billion years later, you'd find half of your U-238 had turned into lead, because that's the half-life of U-238, but even more of the U-235 had turned into lead-207. That would be 6.4 half-lives. So if one half-life of U-238 is 4.5 billion years old, then 6.4 half-lives is also 4.5 billion years old. They agree. That zircon crystal must be 4.5 billion years old. And that turns out to be the oldest zircon crystal we can possibly find. In the Jack Hills of Western Australia, we find rocks that are 4.4 billion years old. Or that is, we find crystals. Now, the crystal originally formed in an igneous rock, but it could be found in a sedimentary rock that formed much later. If, however, we want to know the oldest possible date of the Earth, we shouldn't look at rocks that are easily changed by the rock cycle. We should look at something formed at the same time as the Earth and the entire solar system, and that's meteorites. So by dating hundreds and hundreds of meteorites, we find the same age, somewhere between 4.53 and 4.58 billion years old, and that is the age of the Earth. Well, we can use radiometric dating to find out more than the age of the Earth. We can use it to find the age of rock layers. So here are the isotopes that we use. Our two uraniums, found in zircon and apatite, but also potassium and rubidium, found in muscovite, biotite, and hornblende. Now they all have very, very long half-lives, which makes sense because they formed back in some exploding star that gave its material to the formation of our solar system. And they're still around because their half-life is so long. But what about carbon-14? It has a tiny half-life, not even 6,000 years old. Where did that come from? Well, it's getting formed as we speak, because cosmic rays are hitting particles and creating nitrogen-14 to turn into carbon-14. And that carbon-14 can be found in the carbon dioxide that is in the air you're breathing right now. Of course, that carbon-14 can be brought in by the process of photosynthesis to a tree. And if you go and eat that tree, those organic molecules in the tree have the same amount of carbon-14 as the tree had, as the air had. How much is that? It's a small amount of all the carbon, but it's enough so that we can measure it. All living things on Earth right now have this amount of carbon-14 in them. However, when we die, we're no longer taking in new carbon-14, and what happens to our old carbon-14? It decays. Over time, the carbon-14 goes back into the nitrogen-14 that it came from. So older fossils have less and less carbon-14 than young ones. When a tree is initially buried, it has all of its carbon-14, but after a number of half-lives have elapsed, it'll have less and less. If you found a woolly mammoth tusk, you could use carbon-14 in it to find out that it was 15,000 years old. But what about this trilobite? It's got calcium carbonate, so plenty of carbon, but would it have any carbon-14 left after 440 million years? No, it wouldn't. So what do? You're going to have to rely upon relative dating and absolute dating of layers above and below it. If you can find a layer of igneous rock, either a lava flow or volcanic ash below the layer, that could be dated to 545 million years, and above the layer, 520, you have just bracketed the age of that trilobite, even though you didn't know the amount of carbon-14 in it. In this way, we can use the absolute age of some layers to augment what we already know about the relative ages. Well, folks, that's it. Our time is up.